Alrighty, let's take a look at number one here. So a 63.0 kilogram astronaut is on a spacewalk when the tether line to the shuttle breaks. Um, mission control to Tom. That's a song. Never mind. Okay. The astronaut is able to throw a spare 10 kilogram oxygen tank in a direction away from the shuttle with a speed of 12 meters per second, propelling the astronaut back to the shuttle. Assuming that the astronaut starts from rest with respect to the shuttle, find the astronaut's final speed with respect to the shuttle after the tank is thrown. Okay, so we have a couple of things to consider here. We are still thinking about conservation of momentum. We're looking a little bit more in the realm of that bumper car scenario that we considered yesterday, but this is actually going to be the opposite of that, as opposed to two objects having some momentum and then coming into contact. Here, basically have an astronaut throwing a tank to generate momentum in the other direction, right? Throw the tank that way, it now has momentum in that direction. Well, you can't just magically make momentum out of nothing. That has to be balanced out by momentum in the other direction, right? So that's actually going to propel. Throwing something in one direction propels you the other way in a space situation. So, oh, it's just a whole bunch of rigmarole. Don't even worry about it. You'll be dead by the time it matters.
That's a relief.
I know, right? Takes a couple billion more years. All right, so step one. We want to recognize that we are dealing with a conservation of momentum problem here, meaning there are no external forces going on. The contrived nature of the question creates a situation in which there's no external forces, meaning that the total momentum before the throw is going to be the total momentum after, right? That's why the setup is the way it is. So let's write down the stuff that we know. All right, we have the mass of the astronaut coming in at 63.0 kilograms. We have the mass of the tank coming in at 10 kilograms. And we know that the velocity of the tank is going to be right. And so I've included a plus sign just so we can establish a frame of reference for directions there. You could just as easily call that negative if you wanted to. You just have to indicate that the opposite direction is positive, right? Now, we do know that the initial momentum is equal to 0, meaning everything is at rest. Right? These are the things we know going into this calculation. So we know that the total momentum is 0. So that means that, which is equal to 0, is going to be equal to the mass of the astronaut multiplied by the velocity of the astronaut plus mass of the tank. Oh, sorry. Multiplied by the velocity of the tank. All right. So here we're going to be solving for, what are we solving for? Astronauts' final velocity. So we're going to be solving here. So we're going to rearrange this equation using some of our algebra skills. All right. So we're going to get velocity of the astronaut going to be equal to, and this is all going to be negative because I have to move things around, mass of the tank multiplied by velocity of the tank, and then we're going to divide by mass of the astronaut. Right, so I know a bunch of these things. I don't know, like these three things.
Would it be better to like shorten it to T and A?
No, because my choices are always correct. Even if they're aesthetic, they're always better than yours. So just remember that.
But space.
I mean, but if you in your little world you want to do that, feel free.
Oh man.
Yeah, the subscripts that I've assigned here are they're completely arbitrary. They're only designed to help me keep track of the terms, and so if you don't use the exact same ones, it doesn't matter, right? You're supposed to be keeping track of your terms, and so however you want to label them that helps you, that's totally fine. Right. So what was my mass of the tank? 10 kilograms. Multiplying by 12 per second. And my other value is 63 kilograms. My calculator tells me that that is negative 1.90 meters per second. Okay? Now, what does that negative mean? Remember, we created a frame of reference in which the direction that the tank is moving is considered to be positive. Remember, positive doesn't mean positive in the sense that like it's a good outcome, like, yay, we want the astronaut to get back to the ship, right? No, that's not what we mean by positive. We're just establishing a direction, and so you could just as easily have made the direction of the tank after it's thrown to be negative as well, right? That's totally arbitrary. All we need to do is be consistent in the way we use the sign conventions here. And so because my final answer comes out to be negative 1.90 meters per second, what that means is the astronaut, wait, it's not GHT, right? It's just T. I knew that. Boom. Okay, yeah. Astronaut moves in the opposite direction of the tank at 1.9 meters per second. So if you're ever stuck in space, like Major Tom, make sure you throw something in the opposite direction, and that can actually propel you back to the ship.